So the A times B interaction is the extent to which differences in the levels of factor A are the same at each level of factor B. In this example, the interaction asks the question, is the pattern of differences you get in injury severity scores between low activity Wii games and high activity Wii games the same at each of the 3 different levels of alcohol? Or conversely, is the kind of difference that you get between the 3 levels of alcohol the same for low activity Wii games as it is for high activity Wii games? If there is an interaction between the 2 variables, it means that one can't properly be interpreted or can't be properly interpreted without consideration of the other. Because the definition of an interaction is that the effect of one independent variable depends on the levels of the other independent variable. So how do we go about analysing interaction? Today, to do this, what I want to do is step back and explain family-wise error first within the context of an ANOVA or within the context of a factorial ANOVA. Now let's say I was working in a clinical setting and I was interested in comparing a placebo to low dosage to high dosage medication and looking at how that influences or has an effect on the symptoms of depression. So in this case there are 3 levels of the independent variable: placebo, low dosage and high dosage. So why not compare each dosage separately? I could compare placebo with low dosage. I could compare low dosage with high dosage. Or I could compare placebo with high dosage. Now I could do a bunch of t-tests, but this would not be correct because I would not be able to control for family-wise error. Let me explain what family-wise error is. If I was to buy 1 lottery ticket and you were to buy 2 lottery tickets, who has more chance of winning? It's not a trick question. You would have more chance of winning, and it's probably going to be about 2 times more chance of winning. If you bought three lottery tickets and I bought 1 lottery ticket, you'd probably have about 3 times more chance of winning. Well, it's the same when we conduct tests over and over. When doing a test, we apply an alpha level of 0.05, and this is our criteria for accepting whether the test is significant or not. And when we use that alpha level of 0.05, we're saying that there's a chance, there's a 5% chance that we're not going to get it right. 5% chance that we'll make a type 1 error. So you should only make a type 1 error 5% of the time. In other words, you're accepting something to be significant when in reality it's not. But if you do lots and lots of tests, a little bit like buying lots and lots of lottery tickets, so if you do lots and lots of tests on the same data, then those probability values, they accumulate. So if you had a placebo, low dosage and high dosage, you would have 5% error when you compare the placebo to the low dosage, a 5% error when you compare the placebo to the high dosage, and a 5% error when you compare the low dosage to the high dosage. So across the general hypothesis that there are differences between the dosages, all of a sudden we've got 3 lots of 5% error. This creates what's known as family-wise error. In other words, we start with a 5% chance of committing a type 1 error, and then we do 3 tests, and we've increased this type 1 error to almost 3 times, to almost 15% chance of committing a type 1 error, which is clearly not acceptable. And now imagine if there were several comparisons, like what we're doing in our factorial ANOVA. All of a sudden, the chance of a type 1 error blows out, or it becomes close to 40% if we're doing several tests, which is way above the 5% that we've already just deemed acceptable. But in the case of our example, when identifying what is happening with an interaction, we require analytical comparisons, but we need to control for that family-wise error. All the various analytical comparison tests use different adjustments that try to strike a compromise between controlling for type 1 error, but also keeping a reasonable level of power. Now, the simplest way to control for family-wise error is a Bonferroni adjusted alpha level. That is our normal alpha level adjusted for the number of tests that we do. And we use this new figure to determine if the result is significant or not. All the various analytical comparison tests use different adjustments that try to strike the compromise between type 1 or controlling for type 1 error and keeping that reasonable level of power. Now, identifying what is happening with an interaction requires analytical comparisons, but not all possible comparisons that we're going to be doing or that we need to do or that are available are meaningful. The only problem with this is that it's too conservative with a large number of tests, so making it very difficult for any difference, no matter how big, to achieve significance. So we have to be quite strategic in what comparisons we actually want to make. If you look at the comparisons we can make in interpreting the interaction, not all comparisons are meaningful, as I said before. For example, there's little point in comparing 0 drinks and low activity, or so the 0 drinks low activity, with 4 drinks high activity, because if we find a difference, we can't interpret it. Is it due to the number of drinks or the level of activity? We cannot tell because the two independent variables are confounded in this comparison. Because we waste power comparing everything with everything, we need to take a more systematic approach to analysing interactions. Generally, this more systematic approach is done through simple effects analysis. Now, there are other ways of analysing interactions, but I think it's fair to say that the simple effects is probably the most common and straightforward way. And a simple effect of an IV or an independent variable is the effect of one independent variable at one level of the other independent variable in the factorial design. So a simple effect of a factor is its effect at only one level of the other factor in the factorial design. In our example, can you think of the simple effects of alcohol? Well, there are two. The simple effect of alcohol at high levels of Wee activity and the simple effect of alcohol at low levels of Wee activity. In our example, can you think of the simple effects of activity? There are 3 of them. It's the simple effect of activity at 0 drinks consumed, the simple effect of activity at 2 drinks consumed, and the simple effect of activity when 4 drinks are consumed. A simple effect is the effect of an IV, or a simple effect is the effect of an independent variable at one level of another independent variable. So here we're looking at the simple effect of alcohol, but only at one level of activity, low activity. So here we're looking at the simple effect of alcohol, but only at one level of activity, in this case, high activity. Now you should be able to see that the simple effect analysis is just a one-way ANOVA. The only difference is that the denominator of the F ratio, it uses the error mean square from the full factorial ANOVA. That's if the homogeneity of variance has not been violated. So here we're looking at the simple effect of Wee activity, but only at one level of alcohol, 0. Here we're looking at the simple effect of Wee activity, but at only one level of alcohol, 2 drinks. So here we're looking at the simple effect of a Wee activity, but only at one level of alcohol, which is 4 drinks. So you can see that there are, in total, 5 simple effects in this factorial ANOVA. Do we need to perform all 5 simple effects in this example? Sometimes you may want to when both independent variables are of equal theoretical importance. But the more tests performed, the more family-wise error becomes an issue. And the more severe a Bonferroni or Schoedak correction needs to be made with a resulting less power. The goal is to find an optimal compromise between controlling for family-wise error yet maintaining sufficient power. To maximise power, it's always advisable to be disciplined and to keep the number of tests at a minimum, or at least focusing on what constitutes the primary core of the primary research interests that we're looking at. So post hoc snooping can be done afterwards, but we would not draw any firm conclusions from this, but suggest possible leads for future research. Now, in this example, we're mainly concerned with the simple effects of alcohol, which are the first 2 simple effects. So we might limit our analysis to the first two simple effects listed. That is, the simple effect of alcohol at low activity levels on the Wii and the simple effect of alcohol at the high activity levels on the Wii. Now we decide to keep family-wise error at 0.05. We'd need to use a Bonferroni corrected alpha of 0.05 divided by 2 for each test to maintain the family-wise error at 0.05. To analyse these simple effects in more detail, please see the accompanied SPSS analysis and explanations that exist in the SPSS videos. In the accompanying SPSS video, I run through the analysis of this factorial ANOVA in much more detail and explain the output in much more detail.